Okay, so welcome back. Let's get started. Okay, so before we move on, so you have two more studios left, all right, for your project. All right, so please try to do as much as you can, all right, in terms of software and coding everything beforehand, so that when you come to the lab, you can maximize your time to do all your testing. All right, and like I said, take note of all the things I told you about in terms of keeping your wiring neat, okay, and tightly wrapped around the robot. Okay, don't leave it hanging out or dangling or loose. All right. At the same time, the battery levels, like I mentioned, they need to be mindful that they will play a part, correct? Because we do not have any form of feedback for the motors. Okay, so when you are doing a, a, a movement, right? So for example, the two right turn or two left turn, okay, movement from one grid space to the next grid space is just purely based on your own calibration and your own timing, correct? So you will do your own testing to say that I run my motor at a particular speed for 1 second or 1.5 seconds. I will move from the middle of one grid to the middle of the next grid, correct? So all of that is your own testing, your own values that you put in, and that value will change once the battery levels change. All right, so you have to always mindful of making sure that your calibration, your whatever values you're putting in as thresholds for your IR sensors, everything is done with batteries at high levels. Okay, so that when you go for the competition run, you get these values that represent the actual readings. Okay, and similar for the color sensors as well. All right, how you want to use the color sensor data that is uh, obtained from LDR is up to you. Okay, the method that we did in the studio is one way of calibration. I mean one way of decoding RGB values. All right, the whole idea of color detection is I use my RGB LED to shine on the paper, and the reflected signals that are captured through the LDR will give me a sense of or give me some values which I can then store in a lookup table, correct? And then I can reference those lookup tables when I am doing the actual competition run. All right, how you want to do this in terms of uh, flashing the LEDs in whatever sequence, how you want to do the calculation is all up to you. Okay, there is no right or wrong value for R or G or B. All right, for any of the colors, it's up to you on how you decide to modify the code in whichever way you like. Doesn't matter, as long as you have values that can help you differentiate the colors, that is good enough. Correct, so it doesn't matter your values for RGB is 500, 800 and 900, and your friends is 200, 300, 400. Doesn't matter, as long as you are confident that okay, with these values I can correctly decode, then it is fine. All right, we are not going to compare your RGB threshold values with your other people's threshold values and do any marking based on that. No. Okay, so it's up to you to decide your own algorithm, your own approach on how you want to use RGB values to decode the colors. There is no right or wrong. The studio that we did gives you a good stepping stone, correct? Because that is a proven way of doing it, correct? If you have other ideas you want to try, you can go ahead and try. Okay, there is no right or wrong in this. As long as you can decode the different colors, then it's fine. Okay, so let's get started with the tutorial questions. I'll review first. Okay, yeah. So actually in the past we used to have open access in the night. All right, that means the last 2 weeks the lab used to be open until 9 p.m. All right, but now because of all these restrictions, we are not allowed to do that. Okay, so of course we have simplified your project because of that. All right, so I think it sort of balances out nicely. Okay, so we have more than enough time, all right, to finish up the coding and the testing and everything. All right, so I think should be no issue for any of you. Okay, so let's review the topics we have done. So one of the main things we did this week was on spectral analysis, all right, where we want to analyze a signal in the frequency domain. So this is something different. But all the while we always look at time domain, correct? When we look at any signal, the how the capacitor, transient analysis, the 555 oscillator. So everything was based on timing analysis, correct? How a output signal changes with respect to time. Okay, but now we are looking at it from a different perspective called the spectral analysis. Okay, where we are looking at the frequency components of the signal. Okay, so this is basically gives us a different dimension, correct, of understanding how a signal behaves. All right, because sometimes when you look at a signal from the time domain, it may look very complicated, very messy. You can't really decipher any meaningful information. But when I switch over to the frequency domain, then you may be able to extract out something very meaningful. All right, so it is always good to understand the behavior of a signal in both these domains because they can give you different types of information. All right, so in spectral analysis, basically, so in time analysis, we used to look in this direction, all right, how a signal changes with time. In frequency analysis, now we look at it in this direction. What are all the different frequency components? Okay, what are all the different frequency components, and what are the respective amplitudes of these different frequency components? Okay, so any complex waveform, all right, can be broken down into a infinite sum of sinusoidal waveforms. So that is basically the Fourier analysis or Fourier theorem, correct, where you apply the mathematical approach to solving it. All right, so basically what the scope does for us, it actually applies this Fourier analysis and gives us the result, which is uh, the result of the different frequency components and their associated amplitudes. All right, so by looking at a frequency response like this, all right, we can see that actually there is some noise peak, all right, that it is at a particular frequency that is away from the rest of your actual audio signal. All right, and so this information you may not clearly decipher in a time domain, correct? So if you look at the studio, when you played that audio song, all right, which had a particular noise added to it, all right, some of us may not be able to hear the noise clearly, and even if you hear it, you can't have any meaningful information just by hearing the noise, correct? But if I do the analysis, all right, even if I were to do the time domain, even if I were to look at the time domain respectively, I still cannot differentiate the noise from the actual signal. All right, but if I do the frequency analysis, all right, you can see quite clearly that there is a particular peak somewhere that is further away from the rest of the signal. So that gives you an idea that this is the noise. All right, so with that information you can say, okay, now I want to design a filter that will suppress this noise by a certain dB. All right, and then you can improve the quality of your output. Okay, so that is the whole idea of filtering and so on. Okay, generally filtering itself has complex mathematical operations. All right, so just now one of your friends, okay, mentioned about the MATLAB. All right, so MATLAB is a very popular software tool that is used extensively for a lot of this kind of signal analysis, mathematical sort of uh, computations relating to signals and so on. All right, so it's a good tool to have or to learn a bit so that you know how to do this kind of analysis. All right, and apply some your own filtering techniques and so on to look at how the signal can change. All right, so that is MATLAB. All right, of course, if you look at it from the circuit perspective, there are also a lot of software simulation tools available. All right, so we did not cover all these things in the module. All right, but if you do your search or anything, there are a lot of tools like LT Spice, okay, or P Spice. Okay, so these are all very popular and free uh, what they call circuit simulator tools. That means you can build the circuit like what we did, all right, in the lab, but instead of building it physically, you can actually try it out on your own through the software simulator and plot this kind of response waveforms and output waveforms and have a better understanding of how it works. All right, so these are all things that can help you to design better circuits or develop better code in the future. All right. Okay, so let's go on to question 1. So in question 1, we are okay. So maybe I'll switch. Okay, so we come to the tutorial over here. So in the tutorial question, so the first question is basically telling us there is an audio song from a CD. All right. So this audio from a CD is passed through a low pass filter. Okay, so I have an audio song here. All right, and it's passed through a low pass filter. So I'm passing it through a low pass filter over here with a cutoff frequency of FC equals to 4 kilohertz. And at the output side, I get a signal YT. All right. So what is the minimum sampling rate? Okay. So when you say audio signal, generally, okay, from a CD, what is the sampling rate of a CD audio sample? Anybody can tell me? When you play a CD, a song from a CD, what is the sampling rate used to store audio wave files on a CD? Anybody knows? Yeah, so generally, yeah, correct. It is around the default industry standard is 44.1 kilohertz. All right. So if you were to open up any CD file, you extract out, okay, the wave file, and you look at the properties, you should see it as 44.1 kilohertz. That is the usual default standard that you use to uh, sort of sample and record a song onto a CD. All right. So now what we are saying is, and why we do this, why we use this range is because the audio range of the human ear is what? It's around 20 hertz to 20 kilohertz. All right. Again, most of us are born with this, but along the way, our ears can get a bit degraded. All right, so you can always go and do a ear test on YouTube. Okay, on YouTube you have a lot of these videos where they play different frequencies. All right, or even the app also they have. Okay, so you can try out yourself how good your hearing is. All right. So of course, if you can still hear up to 20 kilohertz, it's very good. All right. If you can't hear up to from 16 onwards or 15 onwards, it is quite normal. All right. So but this is the default hearing range. So in order to make sure that we can reproduce a good quality signal, we sample higher. All right. So that's why we sample at, instead of taking 2 times 20, we take a bit higher, we go up to 44.1. All right. So that is the reason why we sample at 44.1, okay, for the CD signal here. Now, so now when I pass this audio signal through a low pass filter, okay, so you can imagine that my original signal, okay, my original signal is everything from 20 hertz all the way to 20 kilohertz. So it's 20 all the way to 20K. All right, but now I'm sampling or doing a low pass filter at 4 kilohertz. So effectively, anything beyond 4 kilohertz, if I would draw the filter response, it will look something like this. All right. Okay. So anything beyond the 4 kilohertz will be reduced by at least half power, right? Because the 4 kilohertz is the cutoff frequency, okay, which is equivalent to the half power point. That means anything beyond that you would have reduced by at least half the power. Okay. So if I have already filtered the signal, that means when I look at YT, the YT's frequency response will only look something like this. Okay. So this will be the 4 kilohertz. Okay. So if I want to sample, All right. What should be the sampling rate? All right. So of course, theoretically, we say that we take 2 times the f max. All right. So theoretically, the fs should be 2 times 4. So it will give us 8 kilohertz. All right. But we always try to sample slightly higher. All right. Because we, if you sample exactly at 4 kilohertz, what will happen is there will still be some of the signal that you do not want that will be captured. There will be still some amount of aliasing because you still have this portion over here. All right. So again, I will not go into the details of this. This you will learn in other modules. Okay. But basically, at 4 kilohertz, it's not a perfect cutoff. Correct. It is a slope down. Okay. So since it's a slope down, if I sample exactly at 8 kilohertz, what will happen is this sort of remnants that you do not want, some of it can still be present or have some effect in the sample output, okay, which will sort of appear as some form of noise. All right. So to get a better quality output, you usually want to sample a bit higher. All right. So even though it is 8 kilohertz, you can sample higher. So usually we will try to sample as high as we can that is still within the requirements and supported by the system. So you can say I can go up to 10 kilohertz, uh, 10 kilohertz or 12 kilohertz or even 16 kilohertz, doesn't matter. Okay, as much as we can, if we can go higher, we go higher. All right, the higher we go, the better we will be able to get a good quality output, okay, from the samples. Okay, so that is basically the question one. All right. So again, the effect of this additional roll off onto uh, what happens in the sample waveform is beyond this module. All right. But what you need to know is when you sample at a higher rate, you will be able to eliminate the effect of aliasing caused by this part of the signal which you do not want. Right, so that is the reason why you want to sample higher. Okay. Okay, so let's go on to question two. So in question two, uh, a microphone is recording an audio song. Okay. So with a frequency range of the fifth octave. Okay, so the first thing is all these octave values and so on. You are not required to remember them or memorize them or anything. All right. If needed, we will provide it in the question itself. All right. So you don't need to memorize or know what is fifth octave or sixth octave or anything like that. Okay. So in this question here, we are recording audio song with the frequency range of the fifth octave. The song is corrupted by 12 kilohertz noise. This recording needs to be sampled by Arduino Uno for controlling the loudness of the speaker connected to the audio system. Design analog low pass filter to suppress the 12 kilohertz noise by at least 15 dB. All right, so this is quite similar to what we've been doing before. All right, uh, in this case, what we're going to do is we're going to take the approach of just designing it as a passive filter. Okay, so the question never specifically say to design active or passive, so we can choose to design passive. So if I say I'm having a passive filter means the circuit is just basically one R and one C, that's all. All right, where you have your V in and V out. Okay, so so this is your R and this is your C. You can represent as XC. So V out over V in is equals to XC over R plus XC. All right, which is 1 over J omega C over R plus 1 over J omega C, and that can be some represented as 1 over 1 plus j omega RC. Okay, so in terms of representing it in the polar form, all right, we can say this is 1 angle 0 degrees, and this is square root of 1 square plus omega RC square and angle some theta. Okay, so we do not know what is the phase, but there will be some phase. All right. So when we are designing the filter so far, we are interested in the amplitude aspect, correct? How much you want the gain to reduce by. All right. So what we can do is we just focus on the amplitude part of it. Okay. So if I just take the amplitude part of it, so V out over V in, okay, just the amplitude part of it, what I'll get is 1 over this 1 plus omega RC square. Okay, and if I do a log of it, okay, so this is the ratio. If I want it in decimals, then I do the log of it. So it will be 20 log to the base 10 of 1 over 1 plus omega RC square. So these are all the same standard steps that we have been seeing in the past few questions. So this equates to subtraction 20 log to the base 10 of 1 subtract 20 log to the base 10 of 1 plus omega RC square. Okay, so there are two aspects to this. So as you can see, this first term is a constant term, correct? There is no omega here. So this first term, since there is no omega, it does not change with respect to frequency. So this is the pass band gain. Okay, now the second one is this, and this is the change due to omega. Okay, that means when the frequency changes, then this second part of the equation takes effect, correct? And what do we want? Okay, we want a change of minus 15 dB at 12 kilohertz. Right, this is the change we want. All right, so with that we can go on to the next step. So we can say minus 20 log to the base 10 of 1 plus omega RC square at F is equals to 12K must be equals to minus 15 dB. Okay, then we can solve for this. So square root 1 plus omega RC square is equals to 10 to the power of 15 over 20. So RC is 10 to the power of 15 over 20 square minus 1 divided by 2 pi and 12K, 2 pi F. Correct? Okay, and that will give me a RC value of 73.4 microseconds. Okay, so very similar, correct, to the last tutorial, the same steps involved, correct? We are given a particular requirement that I want the noise at a particular frequency to be suppressed by a certain amount. Okay, so the same steps, okay, one by one, they are the same steps. And what we discussed the last tutorial was once you get an RC value, you are free to choose, correct? Generally, if you're doing your own design, you are free to choose any RC value, and you are advised to choose a fixed C and then calculate the R, okay? Because capacitors in the fixed standard values are a lot easier and cheaper to get. All right, getting a variable potential meter is also very easy and very cheap, okay, compared to the other way around. All right, so you can fix a C. So if you just take C to be any value, okay, so in this case, if I say is net 10 nanofarad, you can get R as 7.34 kilo ohm. Okay, if you take C as 100 picofarad, then you get some other value. All right, but you can take any C value and then you calculate the corresponding R value, and that will give you your values that you need for the RC filter over here. Okay, so that part is again quite similar. Okay, question part B here. What is the minimum sampling rate for processing this audio song? Okay, the minimum sampling rate. All right, so basically, if you were to look at it from the frequency domain perspective, okay, you have this signal. So the fifth octave signal is basically from here to here. Okay, so you have the two frequencies here, 523 and 987. Correct. So originally we had a 12 kilohertz noise here. Okay, originally we had a 12 kilohertz noise there, but then we already suppress it. Okay, so it's gone. Okay, with the filter it's gone. So after we suppress the noise, we want to now sample the signal. Correct. So when you want to sample the signal, we can now take the sampling based on the maximum signal component that you have, which is 987. So the sampling frequency will be 2 times 987, which is 1974 hertz. All right. Now, the next question, if we need to design a digital low-pass filter to suppress the 12 kilohertz noise instead of an analog low-pass filter, what is the minimum sampling rate required? All right. So this is again a bit similar to just now in the presentation when one of your friends was talking about the envelope detector. All right, and we saw there is analog approach to it, there's a digital approach to it. All right, so if you take the digital approach to it, means what? So let's look at this signal again, and then we come back to the envelope detector that your classmate mentioned. So if I look at this signal now, if I want to now do the filter operation digitally, okay, so when we say digitally means what? That means I want to take this entire waveform as it is and put it to the digital domain. That means we know that to do this, to go in the digital domain, we must do sampling, correct? So I take the signal as it is, sample it, and once it goes into the microcontroller or into the computer or anything, then I can run my code, run my script, and then do the filter operation later on. Correct. So I must make sure that when I sample the original signal and the noise. All right, I must sample everything in together. Then I do the filter operation over at the software side. Okay, so since I have in the original version, I have a 12 kilohertz noise here. Okay, so if I were to now do everything in the digital domain and I want to sample this entire signal, the F max is 12 kilohertz. All right, which means that I must now sample at 2 times 12 kilohertz, which will be 24 kilohertz. All right, so this again ties back to the envelope detector just now. If I were to do the envelope detector in the digital approach, then I need to make sure that I sample my signal based on the highest frequency of the signal, which is going to be very high compared to a signal that you already pass through the envelope detector and you just see a very nice gentle waveform. Correct. So the original signal has a much higher frequency, correct? So if I were to implement the envelope detector digitally, which means I need to make sure I can sample at that rate. All right, then only it is possible. All right, so this is the sampling frequency that you need, all right, or you need to run at in order to make sure that you can sample the entire signal in together with the noise. And then in your digital domain, you are able to filter out the noise using the software-based approach. All right, so that is basically the idea behind the last question. That means when you want to move to the digital domain, okay, you have to factor in the highest frequency component, including the noise. All right, because the noise will be then handled later on in the software side. Okay, once you digitize the signal. Okay, so of course, the digital filtering is also a highly complex mathematical operation, which you will learn in other modules. All right, so it is again a lot of mathematical ideas involved. All right, and a lot of sort of coding also if you want to implement it in software. All right, but if you, let's say you use MATLAB, for example, MATLAB has a lot of built-in libraries that can perform this kind of filtering operations very easily for us. All right, compared to, let's say, if you were to sample in your Arduino Uno, and then inside your Arduino Uno, you want to design a digital filter. It's a lot more complicated. Okay, because you need to write a lot of software to do it. Okay, so the actual software is actually complex. All right, but if you have library functions, then it can simplify the whole process a lot. Okay, so that is question 2 over here. Okay, so question 3. Question 3 is basically asking us to show that the cutoff frequency is given by this 1 over 2 pi RC. Okay, so how do we do this? Okay, so we are going to take a similar approach, okay, step by step. Okay, so we say that this is your XC, this is R. So V out over V in is equals to R over R plus XC. Okay, which is R over R plus 1 over J omega C. Okay, then what you can do? So the technique we're going to do here is we're going to divide both the numerator and the denominator by R. So you get 1 over 1 plus 1 over J omega R C. Okay, and this will be 1 over 1 minus J over omega R C. Okay, so once you have this, all right, you can actually convert this to polar form. Okay, okay, so these two frequency values 523 and 987 is given by the 5th octave. Okay, so if you search for the 5th octave frequency range, you will get these values. Okay, 523 and 987. Okay, so that's how we get these two numbers. Okay, but like I mentioned, you are not required to know this. If is needed, the information like this will be provided. Okay, so let's go ahead to convert this to the polar form. All right, so V out over V in is going to be 1 angle 0 degrees divided by 1 square plus 1 over omega RC square angle theta. Okay, so again, we are interested in the amplitude. Okay, so we know that the cutoff frequency. So what you want to do is you want to find out that the expression for this cutoff frequency is given by this, correct? And the cutoff frequency is, we also know, is the minus 3 dB point. All right, so that is how we're going to approach this. So we're going to convert this to dB. So this will be 20 log to the base 1 minus 20 log 1 square plus 1 over omega RC square. Okay, so the same thing as before. This is the pass band. Okay, and this is the change due to omega. All right, and then the next step would be to say that this, okay, this change due to omega, what we want is we want this to be minus 3 dB. Correct? We know that this is minus 3 dB at the cutoff frequency. Correct? We know it's minus 3 dB at the cutoff frequency. So we can use that information now to say that minus 20 log to this 1 square plus 1 over omega RC square at F equals to FC is equals to minus 3 dB. Okay, so we can do the next step, which is 1 square over 1 plus omega RC square will be equals to 10 to the power of 3 over 20. Okay, so if you look at this now, how do I do the relationship? You can see that this value here is approximately 1.41. So it is around root 2. Okay, so in order for this thing to be root 2, okay, implies that this term over here, 1 over omega RC must be equals to 1. Okay, so that is how you can find this sort of relationship. All right, and then from there you can solve for this. Correct. So 1 over 2 pi RC equals to 1, 2 pi F RC. So F is equals to 1 over 2 pi RC. Okay, so that is how you can sort of show that the cutoff frequency for the high pass filter is actually given by this expression over here, 1 over 2 pi RC. Okay, so basically that's about it. That's all the questions we have for today. So any things that you all want to ask?
Oh, Mr. Ravi.
Yeah.
Yeah, we do the power for question about question 2. Yeah, question 2 part A. We do the power to find the cutoff frequency is because there's a condition that says it needs to suppress the 2 kilohertz noise by at least 15 decibels, right? Because if
Yeah.
they never give this requirement, can we say that the cutoff frequency would just be the range itself? Like the cutoff frequency would be the 5-octave range of like 987 hertz.
You mean for the
Like if they never give us the condition for the low pass filter, which is to suppress the 12K.
Yeah, I mean if there was no information on how much to reduce the noise or anything, then you can take the cutoff to be the signal highest value of the signal.
Which is 980 hertz for this case.
Yeah. But like I said, usually we will always try to might want to push it a bit further off so that because when we say that FC is at a particular frequency means at that frequency you already have lost half the power. Correct?
Yes.
So in practical sense, usually if possible, we will try to see if we can push the actual cutoff to be a bit further away from the frequencies that you want, because at the FC itself you already have attenuated your signal that you want.
Oh, I think because at the cutoff point the power is already lost already. Like before the cutoff point it's already start to drop already.
Yes, yes.
Oh, I understand. Then another thing would be for the passband gain. Is it like the maximum gain, then you minus off all the filtering gain at the end?
Yeah, the passband gain is always constant, correct?
Yeah.
The passband gain is always a constant value that so when you design a filter, basically within the passband itself, it will always be flat. Okay,
Yes.
and then at the FC is where you have dropped by 3 dB, and then you have a roll off. So that is how. So this gain is always constant. Then the component that changes is where it starts to roll off at FC.
So essentially, all the signal in the passband they gain by the fixed amount.
Yes.
Is that it? Oh, I understand. But then, why is there a minus? Like, why is it minus at the back? I just don't get the formula itself. Like the passband gain minus the frequency, the power gain.
No, because basically this is the ratio, correct? So this is the ratio of the output over input, correct?
Yes.
Then when you look at it in terms of logarithmic, when you do a log to convert to decibel, it is actually a division is a subtraction, correct?
Yes.
Yeah. So this is, you can see, this does not have any omega inside, correct?
Yeah,
There
I
is no
understand.
omega, so that is why this will always be constant. That means it does not change with respect to frequency. Whereas this second component, there is a omega over here. That means this part here will change when omega changes.
Yeah, but I'm not sure. Like, I don't get like what does this mean though? Like this.
This is just extension from this, correct? This
Yes.
part is basically the taking the ratio in the amplitude form and doing a log of it. So by putting it in this form, we are just we are making it more clearer to differentiate what is called the constant, which is the passband, and what is the changing component.
Oh, okay. I sort of get it. Thank you, Mr. Ravi.
Okay, so next week we will still have tutorial. I think that we have uploaded the additional practice questions and so on for you all to try. All right, so all those additional practice questions and whatever questions that you have, we will still have next week's session to go through. And then week 13, I think there is tutorial. I'm not so sure. I'll check the schedule again. Okay, but next week there is still tutorial. Okay, for us to go through the division of the topics for the final assessment. Okay, so the final assessment, you all know the date, correct? Can you all tell me the date? Make sure you all know. Yeah, so it's on the 16th. So previously we said it was supposed to be 14, but 14 is actually on Diwali, correct? So that's why we shifted to the 16th. So please remember that. Remember the timing, remember all the thing, and it will be the same as before, correct? All the Zoom, invigilation, luminous quiz, all of that will remain the same. Okay. So the only thing, take note of the date and the timing. All right. So I think Prof. Vising will send out an announcement on it to make it clear on all these details, plus what are all the topics covered and everything. Okay, so he'll probably send out an announcement sometime in this weekend also. All right, so in the meantime, continue to work on your project. Okay. Again, Monday to Thursday, the labs are fully utilized because of the back-to-back EPP classes. So you can only access during your slot. But like I said, both the remaining slots I will come in earlier. All right, so by 1 p.m. I'll be there. So if you can come in early and start to work on it. Because 5 p.m., unfortunately, we are unable to do any extension. All right, so we have to start closing the lab at 5 p.m. So the only additional time we have is if you come earlier. Okay, so even if your teammates cannot come in. If you can come in, just come in, bring the robot and start to work on something. All right, and then try to do as much as you can. Okay, and while you are doing this one, please remember you also have a report that is due. Correct, the project report that is due. So also make sure you're working on it as well. All right, so that you do not have too many things. I mean, you have a few days, all right, because Tuesday you finish, you still have Friday to submit. All right, so you still have a few days, but it's still good to make sure that is also happening at the same time. Okay, so you don't get overwhelmed with too many deadlines in week 13. Okay, so that's all I have for you. So thank you very much. And I will see you all on Tuesday during the lab session. All right, thank you everyone. Bye.